Okay, so I'll start.
It's a pleasure to introduce the next speaker, Satyen Patel from India. His title is Fedosov Quantization on Smooth Manifolds and Hidden Symmetries. Please.
Yeah, thank you for the introduction. This talk is based on joint work with Dr. Rukmini De. She is also my master's thesis supervisor, so I would like to thank her for inviting me to this talk. And with that, I will begin. The setup is this. We have a Poisson manifold M and a group G acting Hamiltonianly with a moment map rho, which is also a Lie algebra homomorphism from the Lie algebra to functions on M, smooth functions. So the goal is to construct a star product such that these conditions that were already described before by Professor Galasso, these are known as the correspondence principal conditions are satisfied. Additionally, we also want the star product to be G invariant, which means that acting on functions before and after taking the star product should not make a difference. Moreover, there should also exist quantum moment maps, which are again a map from the Lie algebra to functions, but now it's a Lie algebra homomorphism with the star commutator. So this property is satisfied. And you would notice that in general, this is not true because on the left side, there are going to be additional higher terms in H bar, which do not cancel out in general. But if they do cancel out, then we call it a quantum moment map because now we can integrate it to an actual quantum group action. So this is what we want to construct. What is known is Maxim Kontsevich in 2003 famously proved that star products exist on any Poisson manifold. This he used formality to prove, and he gives an explicit construction, but that is hard to compute because it's basically a perturbative expansion of a path integral where we need to compute graphs and then integrals to get their weights and so on. So it's hard to track what happens with symmetries. Then Boris Fedosov in 1994 gave an explicit construction with a formula using Weil bundles. Again, it was talked about before, but this only works for symplectic manifolds. Then Esposito et al. Recently, they showed that star products admitting quantum moment maps always exist using something called G adapted formality, and they require a condition known as equivariant projectivity. So this I'll talk about a bit more later, but our approach is this. We embed the manifold into an ambient symplectic manifold. So because it's symplectic, we can now quantize using Fedosov's construction and then descend the star product to the Poisson manifold that's embedded. So I'll give a schematic of what we'll do. Take a symplectic manifold X, and there is a fiber bundle over this known as the Weil bundle. It's an infinite dimensional vector bundle, and this is part of Fedosov's construction. He shows that there is a map from functions here to sections of this Weil bundle. Additionally, there is a connection he constructs called the Fedosov connection D, whose kernel, meaning the sections which are flat with respect to this connection, are in bijection with these functions. And this bijection map is called sigma. So sigma inverse is going to lift functions here to flat sections of D. And there is also a natural product algebra structure on this Weil bundle, which is non-commutative and associative. So if we pull back this algebra structure via this bijection, we get a star product on the manifold. So this is Fedosov's thing on symplectic manifolds. We would like to have something similar for our Poisson manifold, like a Weil bundle and a map, so that we can descend an algebra here. But this is not possible directly because this requires a symplectic connection to exist. And as you might know, there is no connection which preserves Poisson bivectors in general Poisson manifolds. So what we need to do is go in a roundabout way. We first embed M as a Lagrangian submanifold into a formal symplectic manifold of double the dimensions we call X. And this is also the formal groupoid, symplectic groupoid that integrates the Lie algebroid corresponding to this, to the Poisson structure of M. And so then when we have this symplectic manifold, we can do Fedosov's construction. And we descend this by splitting this Fedosov connection into parallel and perpendicular components. This perpendicular component, deep perpendicular, its kernel is analogous to this. So then we can get a map from here to here, which we can then extend from this to this. And the nice thing here is that we get a square of algebra isomorphisms. And using this square, we can descend the algebra structure here to here. And this also gives us explicit formulas, so we can see how the symmetries are transferring explicitly. So I'll talk about how this works first. In the local picture, we are working in a formal neighborhood. So we are not globalizing as of yet. It can be done um, using jet bundle arguments, but we won't talk about that in this talk. So local picture is there are coordinates xi and x alpha. I, the Latin coordinates are tangential to M, and x alphas are normal to M in the x in X. So then we choose functions omega and gamma on X satisfying this property. Recall this pi ij are the coefficients of the Poisson bivector on M. And this condition, along with this rank being n, I alpha rank being n, and omega ij equal to 0 means that M is embedded as a Lagrangian submanifold into X. Now there is always a trivial solution where we just take Darboux coordinates and take gamma to be pi ij shifted. This always works. But we want to consider gamma to be not trivial because later we want to go in the reverse direction. And that I will talk more about later, but you can consider for now to be this as what we are choosing. Then we construct the connection, normal connection, D, using gamma and additional higher coefficients A. These are chosen such that D is flat. We impose D square equal to 0 order by order in the normal directions X alphas to get the values of these and impose D square equal to 0 so that it can be globalized later. Then we prove this lemma that flat sections of D are in bijection with functions on M. This we do using the explicit lifting map sigma inverse. It lifts from here to here, and this function is found. First, we assume arbitrary coefficients, formal power series of the normal variables. Then we impose df equal to 0 along with d square equal to 0. They determine each f uniquely iteratively in powers of x again. And the inverse is obviously restriction to x alpha equal to 0, which means that f restricted to m is just the function we begin with f, which makes sense. Now the sigma inverse is also constructed to be a Poisson map, meaning the Poisson bracket on m is just lift the functions, then take the Poisson bracket on x, then restrict to m, and we get the Poisson bracket on m. And this is what makes the whole descent procedure work even in the quantum case. Now a bit about the Weil bundle. The Weil bundle is again a formal power series in additional variables y, with the capital I being all the coordinates of x. And the product that I talked about is the Moyal product. It's defined like this. If you see the first term here, if you expand the exponential, the first term is going to be just the product of the two functions, two sections. And the second term would be the Poisson bracket. So you can see intuitively that it's a good prototype for the star product on the base that we want. So now he constructs a Fedosov connection using these parts. First is called the coastal differential. It differentiates in the fiber direction. This del is the symplectic connection which differentiates in the base direction, and this R term is chosen so that again d becomes flat, so d square equal to 0. Then we decompose d into tangent and normal directions. Like I said, the d perpendicular would be the part which has the dx alpha in front. So after this, we can show that this is also flat, the perpendicular component, and d perpendicular is a derivation of the Moyal product. What this means is that its kernel, omega w perpendicular, is a subalgebra of the Weil algebra. So this subalgebra is going to be analogous to kernel of D, because the kernel of D was in bijection with functions on M. So this also would be a bijection with the Weil bundle on M. So that's what we do next. Take the Weil bundle on M, which is similarly functions on M with formal normal variables yi with the small I. This is a Weil bundle restricted to M. And define this map now, the phi from sections of Weil bundle on M to this kernel bundle by the image is the unique d perpendicular flat section restricting to the input on the Weil bundle on M. So we show that this is an algebra isomorphism, and the inverse is given by restriction to, again, the y alpha and y x alpha equal to 0. I think this should be just y alpha equal to 0. This should not be there. But anyway, the induced product on this gamma sections of Weil bundle on M is again similar to the Poisson map condition. We lift via phi, take the Moyal product on, take the like standard Moyal product, then restrict to M. And this is our Moyal product on the Weil bundle of M. The proof sketch is we have this recursive equation that we know from the definition of the Fedosov, the d perpendicular, where it's recursive because this occurs here and here also. So, and this delta n is the causal differential of the d perpendicular part. So we start with the 0 degree, this S00, then we put that here and get a first degree because delta inverse raises the degree of y. Then we put that again and get higher degrees consequentially. So solving this iteratively, we know that it's unique. Yeah, so now we can descend everything to M. Define this D bar final connection on WM. By this map, we go via the isomorphism phi, take the D parallel part. We know it's flat by definition, then come back via phi inverse. So this will be the connection, and this connection will give rise to a sigma bar isomorphism map from functions on M to sections of the Weil bundle on M. And finally, we get the star product on the Poisson manifold as lift again via sigma bar inverse, take the Moyal product which we defined, and then come back down. And this is well defined and associative star product on functions on M. Now it also satisfies the correct classical limit because the maps in the middle, the phi and psi inverse, are all isomorphisms. And this f and g are going to be again unique functions on x, which descend like this. And its restriction to M is by definition, again, the Poisson bracket on M. And so we can see that the correspondence condition is also satisfied. Now we talk about the G action. G, we remember, acts Hamiltonianly on M with, there is a classical moment map. And now we want to go from M to X. So assume that there exists a G invariant connection on M. if we assume that, then it canonically induces a G invariant symplectic connection on X. This canonical connection is such that it preserves M as a submanifold, the flows of this connection. So this gives us what we want, a G invariant symplectic connection on X. Then because this, along with all the ingredients in the middle, the phi and the sigma, are all G invariant, we will get the G invariant property that the star product again is G invariant. So yeah, if we compare this, the only assumption we made is that there should be a G invariant connection on M, which compared with E and ST, they require equivariant projectivity, which this is the condition to construct a formal L infinity quasi isomorphism, which is G twisted by this Lie algebra. So this is a stronger condition on the whole bundle to be splitting as a vector associated vector bundle. Now we can lift the classical moment maps the same way. Define the functions J to be the unique functions which satisfy this property, again lifting coming back. Its restriction to M is going to be the classical moment map, and J is also quantum Hamiltonian, which means that its action is an inner derivation, which equals the classical action via the vector fields of the Lie algebra vector fields. So the defect from what we want, what we of the Lie algebra homomorphism is this lambda. If it was 0, then we would have this Lie algebra homomorphism condition. And this lambda was the property shown in this paper by Muller, Barnes, Neumer, that lambda is a constant. It's a constant on X. It's also explicitly given by this capital omega. Omega is a Fedosov central curvature. It's a free term that we can choose that comes up during the Fedosov construction. The main thing to note is that it's a central term, meaning it commutes, Moyal product commutes with all other sections. So this is it explicitly. And because lambda is a map on the Lie algebra, obviously it lies in the second cohomology class of the Chevalier-Eilenberg complex. And if this class is not 0, then that will be our abstraction to quantum moment maps. So what we show as the main theorem is that if omega equal to 0, then obviously omega is lambda, then so lambda would be 0. Then for any Lie algebra, the classical moment map satisfies the quantum moment map condition. If omega is not 0, then if G is semi-simple, and obviously we need G invariant omega, then we can shift the classical moment map by a constant term, A, which we can explicitly compute. And after shifting, then this shifted moment map now satisfies the quantum moment map condition. This A is unique because of Whitehead lemma that both H1 and H2 of a semi-simple Lie algebra is 0. And in general, obviously, if this is not 0, if G is not semi-simple, then the class would not vanish. And if it would only vanish if it's exact, meaning this A will give us the lambda to be the 0 class in this. So for general G, this is the abstraction. Now the good thing about this construction is it also works in reverse. What that means is we can start with a symplectic manifold with a given symplectic form omega. Assume that it's bi-Lagrangian foliated and take one of the leaves to be M. Now we can induce, given an omega, a Poisson structure on M called pi by selecting some appropriate gamma. Then we do the whole procedure as described, and we get the star product on X, which gives us the star product on M. Now note that the G action on X does not necessarily have to preserve M as a submanifold. So, but yeah, we never assume that we need to preserve M as a submanifold, but all we need is that the quantum moment maps to restrict to M. And once it restricts, we have a well-defined symmetry on M with the star product. And we call this symmetry hidden symmetry because even though the moment maps themselves restrict, we don't know if they integrate to any group that is intrinsic to M itself. We need the ambient geometry and the embedding for the group G to act on X itself. And so that's why we call them hidden. So now the natural question is, can one systematically produce such examples of a nice manifold that we want to study embedded in as a Lagrangian submanifold in a symplectic manifold? And that is what the ongoing work we are doing is. Now we choose CPN because, as Professor Spera described, that the Fubini-Studi form provides very nice geometry. Its sections, the sections on the of the line bundle have a nice basis as homogeneous polynomials of the coordinates. So that gives us an explicit Hilbert space on the sections of line bundle, and it also gives us a reproducing kernel using the coherent states. And the work of De Ghosh also shows that if there is an embedding like this, we can pull back the whole reproducing kernel Hilbert space via this embedding to M and get a Hilbert space on M. And then, so that gives us an induced star product after we do Berezin quantization on CPN. So now we are trying to connect these two things, that this paper's Fedosov product is controlled by this omega term in the Deram cohomology. And this gives us an explicit formula. So the Berezin one is controlled by the dimension of M, and this gives us the Hilbert space structure. So if we are able to find an equivalence and relate the two, then we can potentially link deformation quantization and geometric quantization on Poisson manifolds, similar to how Berezin does for Kähler manifolds. Yeah, so with that, I will end the talk. Thank you so much.